stream here. Okay. All right. Well, we'll get started, and it is week 1 Wednesday, and we'll continue on in our discussion of data structures. Here we'll talk about two-dimensional data structures. So we left off on Monday covering vectors, atomic vectors, and lists, and now we'll expand that into two-dimensional structures like matrices and arrays, which are the atomic version of a two-dimensional, So matrices and arrays are atomic, meaning that everything in a matrix has to be of the same data type, okay? And an array is just, matrices are two-dimensional and an array is n-dimensional. And so, whatever we're making, as soon as you put a character into a matrix, it's going to coerce everything in that matrix to be of character type. Okay. Generally, we're almost always working with type double matrices, but occasionally you can have integer matrices and you can have character matrices. But almost always whenever you're doing calculations and whatnot, it's generally going to be a type double matrix. Okay. The way we create a matrix is you can use the argument matrix. You put in the values that are going to go in the matrix, and then you define the number of columns. Okay, or the number of rows. Okay, you can define both for good measure. But if you've got 6 elements in your matrix and you say there's 3 columns, it's going to figure out that there's 2 rows. Okay, it will complain if you try to make a matrix that the number of columns is not a factor of the number of elements, okay? So anyway, the way the matrix gets populated is it's populated column-wise, okay? So if it's 1 through 6, it goes 1, 2, 3, 4, 5, 6, okay? If you want to fill it out the other way, you have to specify by row is equal to true. You can, okay, and then with an array, it also fills out column-wise, then row, and then by the 3rd dimension, and then by the 4th dimension, so on and so forth. So in this case, we've got 12 elements, 2 rows, 3 columns, and 2, layers. And so it would fill out the first layer column-wise, then it fills out the second layer. Okay, that's an array. And you can see the way it shows the columns and rows. For the rows is the kind of the first number, okay, corresponds to the rows. The second number corresponds to the column, and the third value corresponds to the sheet or layer. Okay, so if I wanted to reference element 4 in array B, all right, let's do element 6. Okay, this element 6, this would be 2nd row, 3rd column, 1st layer. Here, we'll demonstrate this. Okay, so here's our matrix. Okay, here is our array B, and if I wanted to get at this element B, I would do B, 2nd row, 3rd column, 1st layer, okay, and that would be the 6, right? If I leave out one of the things, then it will give me 2nd row, 3rd column, and for both layers, so it would return back a 6 and a 12. Okay, you see that? Okay, I would say we don't really use arrays all that often. We like to deal with our two-dimensional structures. Okay, you can also just take any kind of object here, okay, and so a little bit bad practice here. I'm storing C into C. I'm taking the vector 1 through 6. Okay, so C is just the elements 1 through 6. Okay, it's okay because R recognizes that this is not a function. And then I can just say, hey, you know what? I want to give dimensions to C. Okay, so this means I want 3 rows and 2 columns. Give this atomic vector some dimensions. Okay, I do dimensions C is 3, 2, and now C has changed into a matrix. If I ask print out C, there we go. I got 3 rows, 2 columns. 1, 2, 3, 4, 5, 6. Okay. Likewise, I can go back and I can just say, oh, you know what? I actually want 2 rows and 3 columns. I'm going to say the dimensions of C are 2 rows and 3 columns. I do that, and we have this. Okay. And if you want to turn, you can also get rid of the dimensions. Okay. So you can do this. This will keep it as a matrix with 1 row and 6 columns. Okay, and if you want to get rid of it entirely and turn this back into a vector, you can null out the dimensions. Okay, and C is back to a vector. Okay, so all of these are kind of fluid. There is a difference between a row vector, a 1-row matrix, which mathematically we treat as just a vector, right? But there is a distinction because this is an atomic vector with no dimensions, okay? The dimensions of this thing, if I ask for the dimensions of C, it's going to say there are no dimensions associated with C, whereas if I applied these dimensions here, then the dimensions of C do exist, and thus it is a matrix. Okay? So you can modify the dimensions in place and get rid of them as such. Okay, the length function, which returns the length of an atomic vector, generalizes to number of rows and number of columns for matrices. And for arrays, we don't have like number of layers or something like that. So you have to just use dim. Okay, so here, what do we have? Let's go back to 2 and 3. So C is 2 rows, 3 columns. I can say, what is the length of C? What is the length of C? The length of C is 6, but if I want the number of rows, I would say number of rows in C, which is 2, and the number of columns in C, which is 3. Okay? But the length of C itself, there are 6 elements in it, so the length of C will return 6. Okay? We can assign names, row names, and column names. These, just like all the other stuff, those are attributes of our thing, right? So we can always ask for the attributes of C. Okay? Right now, the only attributes are the dimensions. Okay? But we can start assigning names, and I can say the row names. I guess over here we're dealing with A. Okay, so if I ask for what does A look like, now that I've taken 1, 2, 3, 4, 5, 6, and then I've assigned some names to the rows, I've capital A and capital B for the rows and lowercase a, b, c for the columns. Okay, we can see that A now has names, and if I ask for the attributes of A, it says we've got dimensions 2 and 3, and then we have dim names. Okay, dim names itself is what is it? It's a list, right? It's a list, and there's 2 vectors in dim names. So if I ask what's the structure of this thing, of the attributes of A, it says there's a list of 2, the dimensions and the dim names, and dim names itself is a list of 2 with a vector for the row names and a vector for the column names. Okay. So column names will refer to this this element here. Okay. All right, and then we've covered this: the length of A, the number of rows, and the number of columns. Over here is the array with 12 elements. That's what B looks like. The length of B is 12, and we can't. There's no number n row or something like that. So dimensions of B says 2, 3, 2. 2 rows, 3 columns, 2 layers. Okay, and then I guess if you go further dimensions, 4 dimensional, so it would be number of layers, then number of number of prisms, and then number of hypercubes. I don't know what comes after that. Okay, so we have dimension names. If you want to assign names to the dimensions of B, you have to provide it a list, much like this list. Okay, right? This dimension names for a rectangle, okay, is a list of 2 things. Dimension names for a prism would be a list with 3 vectors in it. Okay, so we got 1, 2 for the rows, A, B, C for the columns, and layers A and B. Okay, and so we have something like this. Is that okay as far as the dimension names for an array? Okay. The combine function C is generalized for C bind and R bind, okay, for matrices. Okay, so if you want to combine matrices, meaning kind of just attach them together, you can use any of these things. So C bind is for column-wise binding, and you would take the matrix A, which was 1, 2, 3, 4, 5, 6, and then all you're doing is you're taking another matrix A and you are binding them with respect to columns. Okay, so now we have columns A, B, and C, and A, B, and C. Okay. Again, names, row names or column names do not have to be unique for a matrix. Okay, they're most useful to have unique names, but they are not required to be unique. They're just vectors. They're just character vectors. Okay. If you want to bind by rows, you do R bind, and it just attaches one to the other by row, just like that. Okay, and it preserves your dimensional attributes and things like that. Okay. You can transpose the matrix by using the function t, lowercase t, to transpose. And you can test if an object is a matrix or an array using is.matrix or is.array. Okay. Is a matrix an array? Yeah, it is. Okay. All right, so here is this, and we can say is.matrix A, and that will say true, and is.array A, and that is also true. Okay, so an array, so a matrix is an array that has only 2 dimensions, but an array can have more dimensions than that. If I C is currently a matrix, but if I get rid of the dimensions of C, okay, so C is this. All right, so we can do is.atomic C, that's true. Is.matrix, whoops, that's false. Okay. If I ask is.atomic on A, what will that return? So A is this. So if I ask, is this atomic? What will it say? This will say true. Okay. Atomic is just the quality that everything in there is of the same data type. Okay. Okay. It's not an atomic vector. It's not an atomic vector. So if I do is vector A, that's going to be false. Okay. The is vector will return true for atomic vectors and lists. Okay. So if you want to know if something is an atomic vector, you have to use both is atomic and is vector. Okay. Is atomic will just tell you if is atomic is true, it's either going to be a matrix, array, or an atomic vector. And then if you want to know if it's a matrix, you got to use is it a matrix or something like that. Okay, and you can see, yeah, again, you can test if an object is a matrix also by looking at dim. If dimensions exist, you know that it is not one-dimensional, okay? Do lists have dimensions? Okay, so we'll go to structure of A. Whoops. I'm sorry, attributes. So attributes. What am I doing? Okay, attributes of A is a list, right? So we can say type of attributes of A. That's a list, right? So we can ask, are there what dimensions here? There are no dimensions for a list. Okay, but we can ask, what's the structure of the attributes of A? And we see the structure, but there's no dimensions. It's viewed by R as a one-dimensional structure. Okay, so anyway, that's that. We combine them. One-dimensional matrices, I'm missing a T there. Vectors are not the only one-dimensional matrix. You can have a matrix that's a single row or a single column. They print similarly, but they behave differently, okay? And well, one-dimensional matrices and arrays have the dimension attribute, and so they are still matrices, okay? Right? So if we go back and C looks like this, but let's do dimensions of C is going to be 1 by 6. I'm having butterfingers today. Okay, so C is a matrix like this, and if I ask, is C a matrix, that's going to be true, and is it a vector? Okay, that's false. Okay, now that it has dimensions, even though it is a row, single row matrix, it is no longer a vector. Okay, and it says the differences aren't too important. You can always use structure. Okay, if we look at the structure on this thing, okay, we can tell it's a matrix because this thing has a comma in there, meaning it says there's one row and then 1 through 6 for the columns. Whereas if I just did a structure of the vector 1 through 6, there's no comma inside this thing here. Okay, so when you have the comma there, that means there's kind of 2 sets of dimensions. Okay, with A we can see 1 through 2, meaning 2 rows, 3 columns, 1 row, 6 columns, but it's a matrix. Okay, so here just some examples. 1 through 3 is a one-dimensional vector. Structure is this. The attributes of F, there are no attributes. It says null. Okay, currently no names. If I gave names to F, then that would show up in under attributes, but there's no dimensions attribute there. And is atomic, that's going to be true. Here we have a column vector. Okay, matrix 1 through 3, we're going to say it's one column. Okay, when we look at the structure, it says 1 through 3, comma 1. Okay, so that means we've got rows, 1 column. The attributes of G shows that there are dimensions, and is atomic got cut off, but that's going to be true. Same thing with the row. Okay. This is a quote, an array vector. Okay. It says, is it an array? And so we're taking 1 through 3, and then we're just saying there's going to be 3 rows, okay? And the structure on this thing says there's 1 through 3, it's one-dimensional there. Here, we can mess around with this idea here a little bit. What will dimensions I return? This does exist, okay? So it does have dimensions, attributes of I. It just, the first dimension has a depth of 3, okay, is all it's saying. It feels weird, okay, right? But, okay, so let's back up. Okay, let's do Hi, J. J will be 1 through 12, okay? So J is currently this. And then we'll say the dimensions of J are going to be 2, 3, we'll do 3, 2, and 2, okay? So J looks like this, and if I say, what are the dimensions of J? it's going to say 3, 2, 2, 3 rows, 2 columns, 2 layers, right? Over here, we just said I is 1, 2, 3, and the dimensions of I is just 3. And this looks very much like a vector, but I think if I do is.vector I, it's going to say false, okay? And that is because, again, when we look at the attributes of I, it has a dimensional attribute, okay? And it's strange because the dimensional property of I only has one element, a 3, meaning that there's 3, quote, rows, 3 rows, and no other dimensions, okay, which to us mathematically would seem like it's a one-dimensional vector structure. But the fact that this dimensional attribute exists means it's no longer a vector in the eyes of R, okay? Mathematically, they're like the same, but when it's represented in the computer, this is no longer a vector. It's like a minor point because we don't really deal with arrays all that much, but we can say I is an array 1 through 3 with so this might feel a little bit more comfortable, okay? And we ask what's the dimensions of I? Now it says 3, 1, 1, okay? And so it's represented this way, but this thing back here is still an array, okay? And it just has the dimension of 3 there. Okay, I know, it feels weird. Oh, I guess before I move on to data frames, are there any questions about the atomic matrices and arrays? Yes? How would you access the elements in an array? You access them the same way. We'll have a section on subsetting in a tiny bit here. But, okay, so let's look at, what was the other thing? J. J is the array here. You just access them like you would. So I can say J1, comma, okay? Because you need to provide for all the dimensions, right? So what is J1, comma, going to return? It's going to give me 1, 4, and 7, 10, and what will that be? Would the structure be a vector, a matrix, an array? It's a matrix, okay? Because what you're effectively doing is you've got, imagine this rectangular prism, and by saying I want 1, you are just slicing one layer of this prism, but you're slicing it in whichever, I don't know, whatever dimension it is, right? Yes?
If I want two slices,
well, if you want 2 slices, okay, so you say 1 through 2, what will this return? This will return an array with 2 layers, but just it will have, the top layer will be 1, 2, 4, 5, and then the second layer will be 7, 8, 10, 11. Here, we'll look, okay? Because you're saying, here's my prism, and I want to slice out these 2 rows, or 2, the layers now go this way, right? And then so you're saying that, and so you're doing this. We're playing 3D chess here, guys. All right, but that's what it is, right? Your array structure is, this is a 3-dimensional structure. I don't know, 40 something. Okay. Let's talk data frames. Okay, we got to cover some stuff here. Okay, a data frame is the most common way of storing data in R and is used and if used systematically, makes data analysis easier. Okay. Yeah, under the hood, a data frame is a list of equal length vectors, okay? So if you look at the structure of a data frame, it's actually a list, okay? Before, the generic list could have, you know, the first thing could be a function, and the second thing could be, a character vector, and the third thing could be a logical vector, and they could all be of different lengths. For it to be a data frame, you've got all of these different atomic vectors, possibly a factor, which is really just an integer vector, but you've got these different atomic vectors, and they are all of the same length, okay? And that way, you can display the data frame as a matrix, or as a rectangle, okay? And so the data frame has names, okay, which is going to be the names of the elements in the list, and column names, which will be the names of the columns in the data frame. But names and column names are equivalent for a data frame, okay? And then the row names also, I guess I wrote that. Names and column names are the same thing. Okay, and then row names apply for the rows. The length of a data frame is the length of the underlying list. So for a data frame, the length is the number of columns. Okay, and it says you can subset a data frame like a one-dimensional structure where it behaves like a list, or a two-dimensional structure where it behaves like a matrix. Okay, so here I am creating a data frame. I'm saying x is equal to 1 through 3, and y is equal to ABC. All right, we create a data frame using the function data.frame parentheses, and that's what we throw into there. Okay, and so it goes 1, 2, 3. This is my first thing, and y is ABC. And when we look at the structure of data frame, it says data.frame, and we see it prints out like a list. It says first you got x, which is an integer vector, and y, which is going to be a factor, okay, with levels A, B, and C. Data.frame's default behavior is to turn strings into factors. If you want strings as factors, strings to remain strings, in the creation of data frame, you would have to also say strings as factors equals false, okay? And then that creates the data frame this way, and it keeps them as characters. ABC. Okay, it says a data frame is stored as a list inside R, which is reflected in type of. If we ask type of for the data frame, it's going to say it's a list. Okay. However, if we ask class of the data frame, it will say it's a data frame. Okay. And then we can ask, is it a data frame, by using is.dataFrame, which will return true here. You can coerce an object to a data frame with as.dataFrame. Okay. A vector will create a one-column data frame. A list will create one column for each element. It's an error if they're not all the same length. Okay, so if you have a list where all the vectors are the same length, you can coerce that into a data frame. But if the vectors are not the same length, that as.dataFrame will kick back an error. And then a matrix you can coerce into a data frame. You just say as.matrix will create a data frame with the same number of columns and rows. Okay, basically it just takes those things and throws them into a list. Data frame. You can combine data frames using cbind and rbind, like the way we did for matrices. Right? So here I'm going to take data frame df, which was 1, 2, 3 ABC, and then I'm going to combine it with another data frame which has the column z 3, 2, 1. We can do this with row bind also. Okay, and we do this. Now we've got to kind of define these things tell them that we're attaching data frames to these things. And when you do rbind for the data frame, you have to say, you have to have the columns. X is 10 and Y is, whatever letter that you're using, and they need to match up, okay? If you don't give it the appropriate names to match up, it's going to kick back with an error. No, I guess that's what this slide says. Okay. a common mistake is to try to create a data frame by using cbind and binding vectors together. Okay, that's not going to create a data frame. Okay, if you take vectors and you use cbind, what's it going to do? It's going to make a matrix, and a matrix will coerce everything to be of the same data type because matrices are atomic. So if you've got a character vector and a numeric vector and you use cbind, it's going to make a matrix first and coerce everything into characters, and then you'll be left with that. Okay, just use data.frame directly. Okay, so for example, so this is the mistake here. If we cbind a numeric vector 1 through 2 with a character vector A and B, and we bind those together and then throw that into data frame, it coerces everything into characters, and then when we throw it into data frame, everything gets coerced into factors. Okay, all we do instead, we just go use data frame directly, and we say A is this and B is this. And if we want to turn off strings as factors, then we can do that, and it creates the data frame like that. We'll cover the package dplyr. Have you guys used dplyr yet? A little bit, sort of, not really. Okay. Well, we'll cover that later, like next week or something, or I don't know, maybe even later. And so that's it uses something called a tibble, okay, and it has some nice features, but we'll worry about that later. Okay, so that covers matrices and data frames, and now we can talk about subsetting, okay? And when we talk about subsetting, I'm going to talk about the one-dimensional things first, and then we'll talk about subsetting in 2 dimensions, but that will come on Friday, our next lecture. Okay, subsetting operators, powerful and fast. You've probably done a bunch of subsetting already, but there are a bunch of different topics that kind of intersect, and so in the beginning, subsetting can be a little bit overwhelming, or somebody will do some kind of subsetting that you're not used to, and it'll take a little bit of time to get your brain wrapped around it, okay? But a lot of times, if you look at the structure of an object, it will give you an idea of how you can appropriately subset the thing as well, okay? All right, so we subset atomic vectors using single square brackets, and then we can expand using subsetting with the double square brackets. Double square brackets apply for list type structures, so lists and data frames, right? And then you can use assignment along with subsetting, and then we'll have some important applications of subsetting. That's going to come a little bit later. Okay, so here I've got the element vector x, which is 2.1, 4.2, 3.3, and 5.4. Okay, these values are chosen so that they're not in any kind of order, other than if you look at 0.1, 0.2, 0.3, 0.4, that's kind of the position that they were in the original vector here. Okay, and so if I wanted to subset x, I can say, give me back elements 3 and 1. Okay, I'll do x square bracket, and inside that I give it a vector 3, 1, and it will do 0.3, 3.3 and 2.1. It gives me the third element and the first element. Okay, again, the elements are 2, 1, 4, 2, 3, 3, and 5, 4. If I use the function order x will tell you the vector that you would need to use to put the elements in order. Okay, so this is the ordering of the things. So if you say subset x based on the order of x is 1, 3, 2, 4. When you do that, it will return the first, third, second, and fourth element, which will be in arrangement from least to greatest. So order of x returns the vector that shows the arrangement that you would need to use to order the elements. Okay. The vector that you give it to subset can have duplicated elements. So you can say, give me subset X, give me back the first element, and give me back the first element. And so you'll get 2.1 and 2.1 again. Right? And this feature of the subsetting operations is actually quite powerful. Okay, and then if you give it real numbers, okay, anything with a decimal, they are truncated. They're not rounded, they're truncated. So if you say, give me element 2.1 and element 2.9, they just get cut off. There's no warning, and it will give you back the second element twice here. Okay. If you give it a negative integer, R is going to throw those elements away, right? So if I say subset X with a square bracket minus 3 and 1, it will give me back what X is without the third and first elements, which will just be the second and fourth elements. Okay? But of course, you can't mix negative and positive things, because when you give it a negative, it says, give me X without the first element, and then you're saying, give me the second element. So it doesn't know, do I just give you the second element, or do I just give you, everything but the, it gets confused, okay? So you can't do that. All right, you can give it logical vectors, okay, and so you can say true, true, false, false, okay, and then it will just give you back the elements that correspond to true. All right, so in this case, the first two elements have true and the third and fourth elements have false, so it gives you back the first two elements and it leaves out the third and fourth. Okay, and of course, if you say, give it a statement like x greater than 3, x greater than 3 will create a logical vector itself. Okay, and in this case, it will, x greater than 3 will be true for all the elements that are greater than 3, which is true for the second, third, and fourth elements. Okay, and then so if you say subset x using the results of this logical comparison, give me that back, it will give you back x where the values are greater than 3. Okay. If the logical vector is shorter than the vector being subsetted, it gets recycled. So if you say x and you just give it a vector of 2 elements, true and false, it gets recycled to true, false, and it gives you that. Okay. And then a missing value in the index. So if you have trues and falses, or if for whatever reason your logical vector that you're giving it has an NA, it will always give you back an NA. Right? So it kind of matches it, but then it doesn't give you that thing back, it just gives you back an NA. So it gives you the first element, the second element, a missing, and then it doesn't give you the fourth element because the fourth element says false. Okay, nothing. If you say x square bracket and you put nothing in there, that gives you back everything. It gives you back the original vector, which doesn't quite make sense for atomic vectors, but for a matrix, those are useful. You can just leave out, you have commas to kind of separate the things, and you leave out a certain index, it will give you back everything for that index. And then if you use 0, it returns a 0 length vector, okay? So x is a numeric vector, and if you give it subset x0, it will return a numeric vector of length 0, which basically is an empty vector. It's not the null object, right? The null object is specifically, this thing doesn't exist. But here we have subsetted x to give you back nothing, which, like I recognize in math, you have like the empty set, which we can kind of think as like the null object, but it's a little bit different, right? It's a little bit different. If you have names in the vector, I think this is, we're almost done, okay, for today's stuff. If you have names in the vector, if the vector is named, okay, using, you set the names or something like that, you can use character vectors to return the things with the matching names, right? So here I've got y, we've set the names of x to have a, b, c, and d, and then now I can subset y using a character vector d, c, and a, and it will return back elements d, c, and a in that order. Okay, and just like the integer indices, you can repeat character indices, so you can say AAA, and then we'll give that back, okay? And if you, when you're doing subsetting with single square bracket, the names are matched exactly, okay? So if the names for Z are the names A, B, C, and D, E, F, and you say, give me back the thing that matches A and D, it's going to say, I couldn't find it. That thing is missing. Okay, so it returns NAs. Okay, and that will cover it for today. Okay, that's the introduction of subsetting. Good luck. I hope the homework is going okay, and we'll see you guys on Friday.